In multiple lectures, we've discussed how to actually kind of calculate the reliability of a measure. We've included split half, we've included time one to time two, and other methods that can be used to basically look for the relationship or correlation between a variable with itself. Today, I'm going to kind of go through additionally some methods we can use in the statistical package SPSS in order to do those calculations depending on what we're looking at. And I'm going to talk a little bit about the particularities of every particular technique in SPSS. As always, I recommend that you download these slides and have them available for other classes, other statistics, and just to have them on reference if you're ever having to work in SPSS in the future. So the first thing I want to talk about is computing a test-retest reliability. So this is when we've given the exact same test to the same people, but at two different times. So notice I actually have here time one versus time two in the data set, and that's what I'm going to be comparing at. Again, I'm going to look at analyze, correlate, bivariate, because I'm basically comparing the test to itself over from time one to time two. Once we're in there, I'm going to bring time one and time two over by selecting them and clicking the arrow. And again, this is simply what I named those variables. You can name them pretty much anything that you want. You might call it, you may give it a date. You may actually just say test number one, time one, whatever it is. You're going to take that first test and that second test and bring it over. So again, remember, for this to be appropriate, we have given the exact same test or assessment or measure to the same group of people at two different times. So we have their scores from time one and time two. We talked a little bit about what's the minimum delay time. Generally speaking, we're looking for at least 6 weeks, but there are some situations where that just may not be possible. And we may be still looking at a difference between how people perform for 1 week to next week, for instance. Once we've brought both of those over, we're going to make sure that we flag significant correlations, make sure it's two-tailed, and make sure we've clicked Pearson. These should all be basically the defaults, but make sure they're clicked as you see on the screen, and click OK. This is going to give us our Pearson correlation, our R. So in this case, from time one to time two, we're going to see that it actually has a correlation of 0.671. Now remember that to get our R squared, our effect size, it's 0.6 times 0.6. So it's going to be a smaller number as far as percentage explained. But this is significance. Notice the significance at a two-tailed test is 0.001. So it is a significant test. We have an N of 20. So again, if we were reporting that as a degrees of freedom, that would be N minus 2. So in that case, that would be 18. To compute the alternate forms reliability, what this simply means is that we're basically looking at two different forms that are supposed to measure the same thing in the same way, but we have alternate forms. In other words, there's a form A and a form B with different items. Once again, we're going to go to Analyze, Correlate, Bivariate. We're going to bring over our two different forms. And in this case, instead of time one and time two, I'm bringing over form A and form B. And this may be different people. So form A may be one class, form B may be another. It may be that I had a class of 50 and 25 people randomly got form A, the other 25 got form B. But we can still use the same technique in this case. Once again, we're going to make sure Pearson's correlation is clicked. We're going to make sure it's a two-tailed test, and we're going to make sure that we flag significant correlations, and we're going to click OK. And we're going to get the same information. In this case, we have a very strong indication that the form A and form B are actually very much measuring the same thing. We have a Pearson's correlation of 0.976. So if we actually calculated the R square, 0.976 times 0.976, we're still well above 90% of the variance explained. There's still a little bit of error in there, and we'd expect that with our N. But we definitely have evidence that these two tests are very, very similar. They're very highly related with each other. People that performed low on one tended to perform, basically the performances were very similar. Notice the significance here is listed as 0.000. Just a quick reminder, we never report a P of 0. We would report this as less than 0.001. So we discussed how to hand calculate Cohen's kappa in class and in previous lectures. We can also use SPSS to do this. So in this case, we're going to go to Analyze, Descriptive Statistics, Crosstabs. So that's where we're going to be able to actually run this analysis. Once we're here, we're going to bring the raters over. So for example, the example I had to hand calculate was Dr. Zeus and Dr. Doolittle. So again, bring Rater 1 and Rater 2 over by selecting them and clicking the arrow so that Rater 1 is in rows and Rater 2 is in columns. Once we've done that, we're going to click Statistics. Here we're going to click Kappa, so we're telling it what type of statistic we want it to run, and we're going to click Continue. And we're going to click OK. And we're basically going to get very similar to what we talked about in the hand calculation. We're going to get the actual number. So notice these aren't percentages right now. They're simply in counts. So basically, if we look at Dr. Zeus, we see that Dr. Zeus rated 8 people as neither, and so did Dr. Doolittle. But of the people that Dr. Zeus rated as neither, Dr. Doolittle listed 3 of them as ADD, and 3 of them as ADHD. So that's the level of disagreement. So again, the red boxes represent when they agreed, the green boxes represent when they disagreed, and again, we're going to get that kappa value. In this case, it's calculated for us, 0.3, I believe that's 65, correct. So again, if we were going to report this, this is how we report it. We'd report Cohen's kappa, we'd report that value, and then the approximate significance is 0.008, would be rounded to a p of 0.01. So we've already talked about calculating Combrach's coefficient alpha. I'm just going to go over it here again because I'm just going through the various ways that we can use regression to examine various data sets. So if you were running Cohen's coefficient alpha, you're going to go to Analyze, you're going to go to Score, and you're going to go to Reliability Analysis. And go ahead and click that on an existing data set. Once again, you're going to grab all of the items that are in your scale and bring them over. Note that if you had to rescore some of them as reverse code, make sure you're only bringing over the reverse coded items and not the original items. Once we've done that, we're going to click Statistics. We're going to basically select items, scale if item deleted, and correlations. And then we're going to click Continue. So again, just make sure you click those top 3 items. So descriptives for items, scale, and scale if item is deleted, and we're wanting to look at correlations. We're going to click Continue. Once we're back to this screen, we're now going to click OK, and we're going to get this information. So this is a bigger example than we did before, but here we have an alpha of 0.324. In other words, this is not a good indicator that this is a good scale. It's probably measuring multiple constructs. We can take a look at the Combrach's alpha if item is deleted, and from that, we can look at the very best item. The best item is going to be the item that actually results in the lowest Combrach alpha if it's removed. And the worst item is going to be the highest value. So again, this is kind of reversed. But if we were going through and looking to see how could we make the scale better, if we actually remove question 6, it would actually take the alpha from 0.324 to 0.177. So that's definitely our best item. However, if we pulled out question 10, the scale would actually go from 0.324 to 0.417. Still not a good scale, but definitely an improvement. So now we're going to talk about computing a split half reliability. So this means that we actually have a test where we've only given it once, but we're basically comparing it to itself, odds or evens, for example. So we start by creating a variable to split the items, such as odds or evens. So we're going to, in this case, go to Data, Sort Cases. Once we're there, we're going to select a sorting variable and click the arrow, and we're going to click OK. So in this case, basically, we're bringing over the variable, example, sorting variable time 1, and we're clicking the arrow to bring it over to sort by. We're going to click OK. And then we're going to select all the odd cases, those with 1. So basically what we're doing here is we're telling SPSS to define which ones of our variables are odd and which ones are even. So we're going to cut those items that are actually odds. We're going to select the topmost box of a new variable column and right-click the mouse and choose Paste. Now go to the variable view and rename the variable scores odd. We're then going to just do this again. So we're going to analyze, correlate bivariate, and now we can compare the scores odd versus the scores even. Bring scores and scores odds over by selecting them and clicking the arrow. Click OK. And we're going to get our correlation. So in this case, we're going to find that these 2 items are actually, the odds versus evens were not very reliable. We have a Pearson's R of 0.15, non-significant with this fairly small n, because again, we split the test in half. Remember that we did have an equation we could quickly use if we wanted to determine what would happen if we had a longer test. So again, in this case, let's say we're looking at what if it's twice as big? What if we doubled the number of items? So we know that the R is 0.15, so we'd simply multiply 0.15 by 2, twice as long, divided by 1 plus 0.15, again, the correlation, so 1.15. And that tells us that if we doubled the number of items, if they were still relatively good, we would go from 0.15 to 0.26. Still not a very good scale, but it's a way that we can, again, use this quick equation to kind of decide, is it worth our time to try to come up with more items?